So as we've mentioned so far, sedimentary rocks provide us important clues about what was going on the Earth at the time that these sedimentary structures were being formed. And so in this little clip, I want to talk a little bit about some of the other kind of interpretations that we can make about the landscape by looking at the different kinds of structures that are contained within sedimentary rocks. So let me share my screen, and then this will be our last installment about sedimentary rocks. Okay, so sedimentary structures are structures that are formed during or soon after the deposition of the sediments, and then they become preserved in the rock. And so they can have to do with the different kinds of patterns of stratification, which is basically another word for the layering, the different layers of the rocks, or the different beds within the rocks. So sometimes we talk about sedimentary bed forms. They could also contain like fossil imprints in the rock, and other kinds of structure. So it's kind of a wide-ranging term, but a lot of it has to do with the different kinds of stratification, shapes, and patterns that we see within the rocks. So for instance, this is a picture of the Grand Canyon, and you can see that there's all these different, very distinct colored layers that we can refer to as different strata. We'll talk about more about strata, stratification, and strat columns, et cetera, later on in the semester. But we can, of course, as we already mentioned, learn a little bit about the history of the environment by thinking about what kinds of rocks are in the strata. Is it shale? Is it limestone? Is it sandstone? Are they layered in a particular way that might tell us about regressive or transgressive facies? But we can also look a little bit more closely and see within the strata what might have been going on to accumulate those sediments. So one important law that helps us understand about different kinds of stacking of sediments is something that's called the Stokes law. And we've mentioned this concept before when we talked about the sorting of different rocks. But we basically said that as rocks are moved primarily in fluids, primarily in water being the main fluid that's moving a lot of these things around, although wind is a type of fluid too, we know that the bigger particles, the larger diameter particles, fall out of the fluid first. So the bigger rock, the bigger pebble, the bigger sand grain is always going to fall first. And Stokes' law tells us the velocity, how quickly that material falls out of the water column, has to do with K, a constant. It has to do with the gravity, density, the viscosity of the fluid, and then majorly is influenced by the diameter of that material, and in particular, the diameter squared. So something that is 1 millimeter in diameter compared to 2 millimeters in diameter is going to be kind of exponentially, or something that's 2 millimeters in diameter or 3 millimeters in diameter is going to be exponentially falling out of the water column faster than something that's smaller. And what we see as a result of this is something that's called a graded bed. So within each kind of depositional layer of material, if you look up close, you'll usually see that there's a concentration of larger size pieces. And then on top of that, we have stacked like medium pieces and then finer and finer and finer pieces until that layer stops. And then on top of that, there'll be another layer with big pieces, small pieces, and then big pieces, small pieces. And each of those layers or beds represents a depositional event, and they all have this same grading pattern that has been caused by Stokes' law. And we call these graded beds. So here's another image. And in this case, we have a graded bed where we have these larger pieces grading into smaller and smaller pieces going this direction, going downwards. We know that Stokes' law works the opposite way, where the bigger pieces fall out first and then the smaller pieces fall on top of them. And so we can actually interpret that this landscape must have been completely flipped on its top. And there's different ways that that might happen through folding and faulting of material through different tectonic processes. But we can kind of, again, interpret the history of the landscape by knowing how sediments accumulate within these different beds within the different strata. This also happens a lot in the shallow ocean when we have these basically like underwater avalanches that have a bunch of sediment roll down the kind of edge of the continental shelf down into the more kind of abyssal ocean plain, or abyssal plain it's called. And within these, what are events that are called turbidity currents, what we see is that there are these same kinds of graded bed patterns that form. And there's a particular type of rock, gray, wacky rock, which forms from all these different kinds of sedimentary graded bed forms that form within the ocean as a result of the same principle. So here's some pictures of turbidity currents that are created by a bunch of subsequent different kind of ocean avalanche-based depositional events. Okay, so there's other kinds of bed form interpretations that we can make. Bed forms generally are kind of about the shape of the bed and tells us about how that fluid was deposited. Most sediments are deposited by either water or wind, and so you can see these different sediments that are deposited in Grand Canyon State Park from this kind of old classic photograph taken in 1929. Have these distinct patterns where all the sediments aren't necessarily being laid down horizontally, and these kind of diagonal shape patterns, the way that they're pointing, the direction that they're pointing, the angle at which they're pointing, tells us a little bit about the environment where they form, or the environment in which they formed, and we would call this a sedimentary bed form. So cross stratification is an idea that within a main bed, so here's like a master bed, a contact point between two different strata, there may be a bunch of kind of internal layers that cut across the main layering direction. And so this is the main bedding direction, and then the internal bedding direction is the cross beds. And the direction that the cross beds are pointing tells us about the direction that the fluid was moving at the time that the beds were being deposited. And so if wind is moving in this direction, we can see that the cross beds form these kind of like cornucopia shaped pieces where they are kind of open at the top, and then they form these little like cliffs down that eventually come to a more narrow point in the direction that the wind is facing. So let's see if you can see this animation real quickly. Hopefully you can see my screen. Oh, it's not going to work. Never mind. Let's go back. Wait, how do I go back? Sorry, let's start over here. Sorry. Okay, let's look at this one instead. Stop share, wait, start share. Okay, sorry about that. Okay, so can we move to the next thing? All right, so here's another way to imagine how these sediments accumulate as a result of certain patterns. And so basically, as a little sediment is being blown by the wind along a particular slope, it will kind of pile up on the top of a crest. And then when it gets too heavy, it will start to tip over the crest and then kind of roll down the slope and accumulate on what we would call the lee side, the side that's protected from the wind. And then it, at the same time, or in a very short period of time, accumulates this additional layer that's kind of on the protected side, the lee side of the mini cliff. And then over time, this continually happens over and over again to create these different crossed beds. And so we can see that the bottom of these cross beds is pointing in the direction that the wind is moving, as I just mentioned. Here's some more pictures. We can see this in sand dunes. We can see this in like floodplains and along coastlines where water currents are flowing. And so we can see these different kinds of cross beds, the kind of layers between all these cross layers. We can see these cornucopia shapes, these little like, I don't know, trumpet shapes. No, not a trumpet shape. anyway, a shape where it's pointing towards the direction that the fluid is moving, and then open at the top in the direction that the fluid has been coming from. And so the kinds of ripples that you see in sand dunes and then you see along the beach are examples of how the sediment is moving and eventually forming these kinds of beds. So for example, here is some ripples that you can see at the beach, and you can see that these little cliff faces are the lee side, the protected side, away from the direction that the fluid is moving. So in this case, the fluid is moving from this corner, the top right corner, towards the bottom left corner, and all these little cliffs are the places where new sediments are building out and accumulating over time. And we can see ripples that have been preserved in ancient strata. So this is like a modern intertidal ripple, what it would look like. And then this is 100 million year old sedimentary like sandstone, siltstone layer from New Mexico. They look exactly the same because they formed in exactly the same way. And so again, this is just another example of how these sedimentary rocks, environments, and structures help us interpret what was going on in the past.